Hello. Let's talk about conduction. So, hopefully, you have reviewed the conduction convection radiation video and you kind of get the idea that conduction normally is heat transfer through surfaces or objects that are coming in contact with each other. Okay, so in this particular demonstration here, we're just going to get a little review of the process and kind of how it works. I'm using air particles, and you'll see I've got two sections of air, a red side and a blue side, separated by this orange line or wall. On the left side, we have our red higher temperature particles. On the right side, we have our blue lower temperature particles. I tried to make that similar to how your brain would kind of do that just automatically. Okay. And what we know about the temperature on the left is that if it's higher, the average kinetic energy of the particles in the system on the left side would be pretty high, higher than that on the right side. So all these particles are moving, right? And the warmer things get, the more they're moving and the more they're bumping around and hitting each other and all of that, right? So let's just give these things arrows. These arrows are representing their velocity, and it's totally random. And they can be large or small, it doesn't really matter. But in general, the average velocity, and again, they're moving in random directions and they'll just be bumping into each other and bouncing back in and stuff through the system, right? So you can imagine there's walls around that side of the system. So they'll hit the walls and they'll bounce back in, things like that. You see those arrows are like relatively large on average, right? So again, you can have one particle with a small amount of energy, and then you can have another particle with a lot of energy. But on average, they have a reasonably large amount of energy, especially relative to our right side. So on our right side, things are going to have, on average, a lot smaller velocities. They're not going to move as far or as fast, right? But you might have one that's like kind of big, okay, or something like that, right? So on average, you can barely see that this one even has a velocity. There we go. On average, these particles on the right have much less kinetic energy than those on the left. So we'll say less KE. I know it's been a while since you guys have dealt with energy, or well, kinetic energy, but remember kinetic energy is that movement, right? Okay. So what's going to happen here if we take out the wall? So let's take out this wall right here. That is going to allow a particle like, say, this one right here to bump into another particle like, say, this one right here. So let's say that particle right here and this particle right here are going to bump into each other, right? And when they do, our particle on the left is going to bounce off and is going to have less energy than it came in with. And the particle on the right is also going to bounce off, but it's going to have more energy than what it came in with, right? And that's going to take that energy and it's going to go and bump into these other particles and transfer some of that energy to the other particles. So then let's say you've got this guy right here, and he's also going this way, right? Let's say he's going to bump into this blue particle right here. Okay, they're going to bump into each other. If that happens, this dude, I'm like totally destroying him. There we go. This dude's going to bounce off with some amount of energy, less than what he came in with. And this little dude on the right over here is going to bump in and come, oop, wrong color. Sorry. We're doing it. This little guy right here is going to come off with more energy. And this little particle is going to take this energy and bump into these other particles, right? So what's ending up happening is you have an overall transfer of energy. Let me draw an arrow here. I want to increase the thickness of my line. How do I do that? This is how. Yep. When an overall transfer of energy is moving in that direction, right? And then let's make this go back down. Energy, right? And what kind of energy is it? It's thermal energy. And what's a fancy word for thermal energy? We call it heat. Okay. So the transfer of thermal energy is basically what we call heat. And that's the process of conduction. This can work with solids, liquids, and gases, right? So the particles will have kinetic energy. And the warmer you get them, the more kinetic energy they have, the more they're going to bounce around and hit other things. And they're going to transfer that energy to those other things. So if you have a cold side and a warm side of something, the warm side is going to have a lot more energy. And eventually it's going to start passing that energy into that cold side, right? And what happens is if both sides end up getting to the same temperature, right? So if this were to equal out and the total kinetic energy in both sides or the total amount of thermal energy on both sides ends up being the same, so the temperatures end up being the same, right? So if at some point we say there's no longer a higher or a low temperature, there's no longer a lesser or more kinetic energy, they both have the same temperature. If they both end up at the same temperature, then we're going to be at thermal equilibrium. There's no longer a need for energy to transfer from one side of the system to the other or from any particles to any particles. Now, energy will still be transferring around because they're going to still be bumping into each other, right? But if the temperature on both sides is the same inside of this closed system, so let's say that we had, a box around the outside of this, like I was talking about at the beginning, we put a box around this whole system here, right? There's a box here, it's all inside the box. Then we'd say, okay, if this whole thing is at the same temperature now, we have reached what's called thermal equilibrium. Okay. equilibrium tends to have to do with things becoming balanced or the same on both sides. All right. So that's a really quick rundown of how thermal conduction works. Again, it can work in solids, liquids, gases. So if you heat up a pot on a stove, right, the bottom of the pot is hot first, and eventually the whole pot will get hot. And that is the process of conduction. All right. So there's a review of conduction. Let's put this to use, right? So we know that when any two surfaces, it could be any phase, solids, liquids, or gases are touching, then energy in the form of heat can transfer between those surfaces, right? Depending on which temperature is higher or lower. The thermal energy, the heat, is moving from higher to lower temperature. So let's take a look at this in a diagram. Okay, so over here on the left side of this wall, we've got this material wall, okay, with width D, and we're calling the wall itself A. Okay, that's splitting two sections of gas, or you could consider it liquid, or you can consider it solid. Doesn't really matter. There's this material, right? And the energy that's on the left side and the right side can only be moved by passing through this material. Okay, so on the left we've got a warmer temperature, we're calling it T1, and on the right we've got a cooler temperature, we're calling it T2, and they're in separate chambers. They can't get to each other aside from moving energy through the wall. Okay, so what we want to do here is kind of talk about how we can discuss this material, this wall, in terms of whether it's a good conductor of thermal energy or a poor conductor, which we also call an insulator of thermal energy, right? So we're actually going to be trying to take a look at deciding how does heat move from the left side to the right side. So that's why I've drawn this yellow or this orange arrow here, which we're calling Q. Q is for heat, right? So let's write that down. Q in this case is heat, basically, okay? Then you've got some stuff that we know about for sure. T is time, which is normal for you guys. We know about T1 and T2. Those are temperatures, right? We've also got A, which is this purple thing here, which we're going to call the cross-sectional area of our material. And then we've got D, which is the thickness of our material. So I'll write D equals thickness. Okay. And then let me get this purple A here. So A is basically the surface area of the material. Okay, and that's what works in this formula. Okay, so but let's just talk about this briefly. All right, so if everything on the left can't get to the stuff on the right, right, that means it has to transfer energy by bumping into this material A, right? So if you're going to be bumping into this material A, then the kinetic energy that's in these particles is going to move into this material, and then it's going to, the energy is going to move through this material and then be able to move to the other side, right? So the rate at which this is done is Q over T, right? Heat transfer over time. So how much heat is transferred in some amount of time, or how long does it take for the heat to move from the left side to the right side, right? So if we start at, I don't know, 100 degrees on the left and it's 50 degrees on the right, how long until we're balanced out at, we'll say, halfway between those two, 75 degrees, right? So that's kind of something to think about. Now, what we need to consider is what is the temperature of the left? What is the temperature of the right? What is the thickness of this material, right? Which we've got right here with this letter D. How thick is our material? How much area of this material is actually being exposed to the heat transfer, right? So that's why we're calling it cross-sectional area, or just the surface area, basically. So you see I wrote surface area of material. Okay. So the more of this material that's exposed to the left side, to the warmer temperature, right, to T1, the more of it that's going to start receiving that energy and then start transferring that energy through to the right side. So if you have a larger area, right, then your heat transfer is going to go a lot faster. If you have a smaller area, your heat transfer is not going to go as fast, right? So similarly, if you've got a larger uh, thickness, right, letter D, if this was a super, super thick piece of material, right, then that means it's going to take longer for the heat to pass through this material with everything else being the same, right? So the thicker the material, right, the harder it is to transfer the heat through it, right? Because it has to hit more particles and bump through, right? So if you consider that this is like a solid and it's made up of particles and all these particles are like next to each other like this, then heat would have to then hit this particle, which would hit this particle, to hit this particle, and then move through, right? So the thicker you make it, the more particles that are in the way, the harder it is for that heat to get through. Okay, so that's what D is. It's that distance or that thickness of that material, right? So basically, we've got left side, right side, and this material right here is what we're studying. Is material, which we have in the center here, this green one, is it a good conductor or a bad conductor? We don't know. We'd have to do some math, and I didn't give you any numbers, right? I'm just showing you how the formula works. Now, there's one thing that we've left out, and you can consider. You can call T1 minus T2. You could call that delta T, right? So you can call that delta T or the change in temperature, right? Because sometimes T2 might be warmer, and you always want this number to be a positive value, okay? You never want this number to be a negative value. So you do what you can to make that number a positive value. So if you have to do T2 minus T1 because T2 is warmer, that's what you do. Okay. So really, it should probably honestly be like absolute value of delta T. But let's not worry about that, right? We're in 8th grade. We don't need to worry about that kind of stuff. All right. Now, the one thing that I've left out is K. The heck is K, right? Everyone's wondering, what is K? K is the conductivity constant for that material. And every material has a different constant. Okay. So actually, that letter K right there is what tells us if we know what it is. And we can find this off of a data table because people have run experiments to find this K value for like every material known to man, right? So this conductivity constant is actually what's going to tell us if this material is a good or a bad conductor. So generally speaking, if you have a high K value, then you're a good conductor. If you have a low K value, like getting near zero, then you're an insulator or a bad conductor, right? So there are things that are better or worse conductors than each other. Now, that's the rundown, and we need to practice a little bit. Practicing is for another time right now. Let's just talk about the formula though. So we can actually find K if we have every other value, right? So if I give you how much how much heat is transferred, right? If I give you the heat energy transfer, I give you the time, the thickness, the area, and you have both the temperatures, you can actually calculate K. So it's actually something that we can measure if we do an experiment. And we might try to do an experiment like that during the class that you have when you're in person. But for now, let's just kind of mess around with manipulating some of the stuff in this equation and see what happens. Okay, so let's look at the equation again. Here is that equation: Q over T equals K times A times delta T over D. Okay, where Q is heat in joules, the lowercase t is time in seconds. And actually, a lot of times we talk about Q over T to be like one value, right? So if we say Q over T is one value, it's in joule seconds, which is the same as watts. So if you ever see a number of watts given, that's actually this whole thing. Q over T is equal to, um, or is found in watts, right? So if you're ever given just watts, you can solve it that way. Now, look, I'm not trying to make this hard for you, so we're going to try and keep it as simple as possible, but I want you to try and mess around with some of these things in your head and just kind of think about how they might change. So K is the thermal conductivity constant, and it has weird units, watts per meter degree Celsius. We don't really need to worry about the units for that, okay? A is the cross-sectional area of a material. Again, that tends to be kind of like the surface area that's exposed to the heat transfer, okay? So like if you have like a rectangle, right, like this, really quickly draw a crappy rectangle for you, right? Something like that, right? And on one side is T1, on one side is T2. The cross-sectional area is just going to be this one face, the area of this one face, okay? And that's in square meters or meters squared for those of you who are in algebra, okay? So that's what A is basically. A is that colored in section only, okay? It's not the rest of it, just the one section. Okay, cool. Then underneath that, we've got the delta T, which is the change in temperature, the difference in temperature, which is usually in degrees Celsius, and it's always got to be a positive number, right? So whichever number is bigger, that's what you put first, because it's going to be like T1 minus T2. Then D is the thickness of your material in meters. How thick is your material, right? Whereas if we use the same example as we did before, there's our D, our thickness of our material, okay? So those are the factors that are going to affect your thermal conductivity. And I want you guys just to think about like what happens if D is big, or if the change in temperature is a large number or is a small number, or if the cross sectional area is a large number or a small number. That's the kind of stuff I want you to kind of think about in your head. How does that affect this equation? So, the questions you're going to be dealing with in today's remote work is going to be kind of like, okay, what happens if these numbers are big? And you can just kind of like use the same set of numbers for kind of thinking this out in your head. Don't worry about the units. Just think about what's going to happen to your equation. So I'm going to ask you things like, okay, if cross-sectional area gets bigger, how is that going to affect our overall Q over T, our overall heat transferred per time? So you're going to think about like, how does the left side of this equation change if we increase the A only, right? Something like that. So all you need to do really is just plug in different numbers and see what you end up getting. So you might say like, okay, K is 1, A is 1, delta T is 1, D is 1, and Q is 1, because, if 1 times 1 times 1 divided by 1 is 1, right? Everything's going to be 1 in that equation. What happens if you change the A value? Only the A value. What does our Q over T value become? Okay. So then instead of having 1 times 1 times 1 divided by 1, let's say you have 1 times 10 times 1 divided by 1. This is going to be 10 over here, right? So what happens on this side? 10, right? So the more surface area you have, if this number, this letter A gets bigger, the more Q over T you're going to have. right? We just learned that by looking at the equation. That's kind of, and it kind of makes sense, right? If I expose more of my surface of whatever my material is to the heat, then more heat's going to be hitting it. So it's going to be heating up more, right? It's going to be heating up faster. That's why we use the big burner when we have a big pot, not the small burner when we have a big pot on our stove. Okay. So that's it for this lesson. The next one is going to be kind of using this equation to actually solve problems. So that's it. Go on to your work and try to enjoy yourself.